In this video I'm going to be deriving a general equation for the maximum range that can be achieved by a projectile projected at an angle of theta with an initial speed of u. So I've set up my diagram, and because air resistance is not factored into these calculations, we can assume that the projectile will follow a perfect parabola, a perfect curve, which would be symmetrical from its maximum height to the left and the right, which is a useful thing to know later on in this derivation. Now, obviously, the range that we want is the horizontal range. So if I was to derive this horizontally, look at my horizontal components. I've already done some work on this already, and I've split my initial speed into its two vectors of u cos theta and u sin theta. Well, I know that distance is speed times time, so my horizontal range will be my horizontal component of the speed, u cos theta, times the time taken to get from initial projection to the end of its flight when it hits the ground again. Now, obviously, we know what u cos theta would be if we knew u and theta, but we wouldn't know the time taken to go from initial projection to the end of its flight. But we can get that from the vertical components. So if I look vertically, we can actually employ a Suvat equation here to find the time taken for it to be projected from its start point to the end. So if I just write out my Suvat as my acronym to help you, then I can see, first of all, I don't know anything about S. U in the vertical is given by u sine theta. However, V is given by minus u sine theta. Now, the reason for this is that the speed of projection will be equal to the speed at which it returns, because there's no air resistance. So if something was fired up in the air at, say, 10 meters per second, it will land back at 10 meters per second due to the symmetry of everything. A is given as minus g, because we've taken initial projection upwards to be positive, so gravity is negative acting downwards. And t is the time taken for the object to start and then hit the ground again, which is the time we need to find the horizontal range. So looking at that, we have u, v, a and t, and the only Suvat we have there is v equals u plus at. Now I want time, so what I'm going to do is I'm going to rearrange the equation straight away to v minus u over a, and I'm going to substitute in everything we know. So v is minus u sine theta, u is minus u sine theta again, divided by minus g. Now, gathering like terms on the top, I get minus 2u sine theta over minus g, and the negatives cancel, giving me a value of time as 2u sine theta over g. Now, that's the time taken for the object to be projected and then land back at Earth again, which is also the time we need to find the horizontal range. Now, if you remember, the horizontal range was given above as u cos theta times t. So now I have my t value of 2u sine theta over g, so I'm going to sub that in, giving me u cos theta times 2u sine theta over g. Simplifying that up, I get 2u squared sine theta cos theta over g. Now, you will need to know some of your trig identities here. So I think this is unit 1 and 3. Sine 2 theta is equal to 2 sine theta cos theta. So I can therefore replace my 2 sine theta cos theta with sine 2 theta, giving me u squared over g times sine 2 theta as the horizontal range. And that is a fact that you need to be able to derive. So that's my range in the horizontal.